Hello and welcome to the continuing education series offered by Pentair. Today's topic is water treatment fundamentals. This is where we're going to look at where contaminants come from in water and the basic technologies that we remove those contaminants. And this applies across the full spectrum of applications we sell at Pentair, from residential to commercial. These technologies are all scalable and fit, depending upon size and flow rate, to the applications. So when we treat water, it's all about the end use. Why? As we learned in water as a managed resource, that water is only managed from the perspective of drinking water, as in safe to drink, not optimized water, but water that's safe to drink. Any other application, the water needs to be looked at and managed to meet the needs of that application, whether that is home residential water use for water heaters or restaurant use for beverage and cooking applications, or industrial process water as an ingredient that needs to meet specific quality criteria for whatever they are manufacturing. So the outcome of water is predicated upon the application, but the technologies we select to get it there is based on the source water. So we're installing the tools in between the source water and the application to get that source water to the quality the application needs. So let's take a look at where this all starts. Water, where do water contaminants come from? It's all a part of the hydrologic cycle. What is the hydrologic cycle? Essentially, this is the process in which water is 100% recycled in nature. The earth essentially mimics a terrarium, a glass terrarium, where it's sealed off and you have a closed ecosystem inside our atmosphere with some energy from the output from the sun to fuel what happens inside the terrarium. That's, the context of our ecology here on this planet. So water is evaporated from whatever surface, whether that's lakes, rivers, streams, plants, exhalation of animals, decomposition of material. All water in our environment is 100% recycled via rapid evaporation. As water evaporates, it loses all its contaminants as it rises into the atmosphere. And when it's up in the atmosphere, it forms familiar shapes that we know as clouds. This is condensation of water vapor. And while it's up here, it starts to do what water does. It's a solvent. It will start to dissolve and incorporate dissolved gases from the atmosphere and dirt and debris, and it becomes slightly acidic, and it rains down across all of the surface of the planet, running downhill, dissolving rocks, organics, anything it can come in contact that it can dissolve, it will. And eventually that ends up in our drinking water supplies. So when we look at this, understand every drop of water is 100% recycled. What differs is what contaminants get into it after it rains down upon the earth. And that's what we're managing. The great thing about this is this makes our industry more of a contaminant management than water management. And our issues are constantly recycled through this process. So the water market will never go away. It's only going to expand based on use. So where do these contaminants come from? Well, our municipalities draw water, whether this is a town or even your home well. Same issues apply here. But most municipalities will get their waters from either underground aquifers or shallow wells. And those shallow wells may be next to lakes and streams and rivers in the saturated soil area around those bodies of water, or they may take it directly from the water source itself, from lakes, rivers, streams, even desalination plants in oceans, or they may take both. They may take well water and surface water, where they may switch back and forth, or they may blend those. Those decisions are made at the treatment plant. And normally those are beyond the control of the market that plant serves. Those decisions are based on health concerns and infrastructure management of the water distribution system, not the use that water's put to. As long as it's safe to drink, it goes into the pipe. So understand that it's not being optimized for whatever applications we may be putting it to. So underground aquifers. When rain picks up, water picks up those dissolved gases in the atmosphere, CO2, carbon monoxide, hydrogen sulfide, just sulfur gases, those sorts of things, as they're dissolved in water, become acids. And when that water rains down, that slightly acidic water, around a pH of 5, rains down over our planet, dissolving all the rocks and things that it can dissolve. That ends up with mineral contamination in the water from the acidic portion of that rain. That dissolves the rock, neutralizes the rain, and now the water continues to absorb or dissolve other contaminants as well. And all of this stuff that ends up as a salt that is charged ionic in the water becomes part of TDS, total dissolved solids. And the interesting thing about water is that the calcium and magnesium carbonates that form scale that are problematic for us don't want to be in the water in the first place. It took that acid precipitation to dissolve rock to get it there in the first place. And it wants back out. Okay? Calcium carbonate and hardness really doesn't want to be in water any longer than it has to. And the interesting thing about this is the dissolving of carbonates from granite or rock strata is the largest point source of CO2 in our environment, comes from this cycle. So CO2 is a natural part of this cycle. We exhale it as CO2 gas, and we convert that dissolved CO2 gas from the rain into acid rain, which converts it into carbonate in the rocks. So it's a connected cycle. All these processes are connected. Dilution and deposition of rock is predicated on water's chemistry. So very interesting stuff here. Now, also part of some of the issues that come up with underground aquifers, depending on how deep they are, and depending on how much dissolved oxygen is in them, you may have environments where anaerobic bacteria that survive by not using oxygen. They use minerals like iron or manganese. These bacteria will feed on those things and produce hydrogen sulfide gas as their byproduct. How we exhale carbon dioxide out of our lungs and our body processes, these bacteria produce hydrogen sulfide gas, which is that rotten egg smell. Now, this is a situation where you can manage the bacteria or you can manage their food source. Either way is a viable method to remove this bacteria from aquifer sources. And this stuff does end up in municipal sources as well. Why? Municipal treatment is a cost-benefit ratio. And if the smell of the water isn't a health effect, stinky water is okay under that standard. So understand that it's very subjective in regional water qualities, the impact of what's allowed to be delivered. Now, where do other contaminants come from? Well, lakes, rivers, and streams, well, that rain, sometimes we get more of it than we would like. And even in a gentle, normal rain, that water is washing over all of present humanity and all the history contained in our soils as it percolates through. With the surface water, it runs off into lakes, rivers, and streams, sometimes causing flooding, right? So this river could be your source. The well punched right next to the river could be your source, this stuff percolating through. Or it may end up in your lake that is your source, adding to its overall contamination or stuff we need to manage. This can be dirt load, chemical load, mineral load. All of humanity is being dissolved by this rain and ending up in our water supply. It's the importance of our industry. So you get gases, sediments, organics, and all of this eventually runs off. Other things as a result of all this organic material entering our streams is biological growth, such as leaves, decaying animals, the byproducts of organic life like bacteria and algae and things, their waste products are there. And then there's things like algae blooms. And, this is a picture of Lake Erie from 2019 of a blue-green algae outbreak. Now, some algae are harmless. Some algae are not. This algae, this particular strain of blue-green algae, produces a toxin to protect itself from things that eat it. This kills fish, and it's also a neurotoxin, and consumed in large enough amounts, this can actually kill people, either from just bathing in it or consuming it. So this is a very natural hazard that exists in many of our water supplies. And then on top of it, you may have just the suspended debris in the water from runoff or wind-driven storms stirring up mud and things like that, like cysts or tiny dirt particles, or even rust coming off of runoff of industrial processes, or as it dissolves the material in the rock strata. And then there's also the potential for chemical industrial pollutants here. What I love about this picture is you get Detroit here, Cleveland here, this is Lake Erie, and this is Canada right here. You're talking about a shared body of water that's shared by multiple nations here for its water sources. But you have all the collective humanity and industrial processes of man that are being not only discharged directly into the lakes after treatment, but are also running off. And it's not just today's contamination. It's whatever's buried in the ground through all human habitation. So we have our water sources are just as much of a source of life as they are in process and ability in our societies, but they also serve as our waste systems as well. Or natural organic systems like lakes, rivers, and streams make great contaminant filters and condensers. So it helps us eliminate pollution naturally in these waters, but we have to manage the outcomes of those. That's where water coming into our municipalities, our wells, needs to be managed. Lots of infrastructure runoff. The Cuyahoga River that feeds into Lake Erie at one point in time in the late 70s and early 80s used to catch fire on its own from all the chemical pollutants in it. We've come a great long ways since the 1970s with the Clean Water Act and the Safe Drinking Water Act to improve our water resources in North America. And actually, we lead the globe in purifying our natural resources. Yes, this is an ever ongoing problem. Why? Because the hydrologic cycle continually purifies and then replenishes this contamination naturally. It's going to rain over the earth and add more contaminants every time it repeats that cycle. So understanding this is beautiful job security for us. So other contaminants that are introduced intentionally to our water supplies happen at municipal water treatment plants or in your water treatment system in a residence. But from a commercial perspective, we're dealing with the municipal water specs that are being treated, how that water is being treated, their sanitizers, their flocculants, their treatment chemicals are all introduced to benefit the water supply. Here's the big but that goes along with it. Chlorine, chloramine, chlorine dioxide, hydrobromous acid, the chlorine analog, are all chemicals that are designed and used to destroy organics and kill biological life. These are potent, strong, oxidizing compounds. They help us rid municipal waters of metals, bacteria, virus, organics we don't want there. But we're making a trade-off here. Why? Those things are toxic to life. But the bacteria and waterborne illnesses pose a much greater threat long-term to humanity than the slight increases in cancers and intestinal issues and those sorts of things that may arise from long-term exposure to sanitizers because they're in such low dose. Yes, we will make this trade every day for a slight increase in cancer versus catching cholera and dying. And that was really a relationship at the beginning of the 20th century that was common. And it still happens around the world today that people experience waterborne pathogens every spring and summer that make a lot of people sick and even kill a lot of people even today. We are blessed with the chemistry of sanitizers to protect our water supply. But like with any chemical tool, there is good and bad with it. I want sanitizers in my system up until the point I consume it, and then I want it gone. Why? Because I'm not a bacteria and virus, and I don't want to be sanitized. Other compounds that are introduced at municipal water treatment plants tend to deal with particle load management, dirt load management, and those are flocculants and coagulants. These are added in excess, and quite often these will make it downstream in the distribution system to your dispense point. Well, these flocculants do not stop working. They coagulate particulates together and stick them together and they essentially make any filter after them more efficient at removing debris, which can lead to premature clogging of filters. Not failure. The filter's doing its job. It's just the chemical that was introduced by the water treatment plant makes that filtration more effective and therefore shortens its life. But this helps improve dirt load. Why are we focusing so much on dirt load at municipal water treatment plants? It's because bacteria and viruses can hide behind the dirt. We remove the dirt, treat the bacteria, sanitize it, get it out into the marketplace. That's the real goal of municipal water treatment. And then there's the notion that, we have sanitary distribution systems, not sterile. Now, there's a reason why you've never seen a biohazard tent erected around a water main repair job, right? We count on that sanitizer to keep our plumbing sanitary, not sterile. What that means is we suppress biological growth enough to a point where if there are any pathogens still alive in our water supply, your body has the ability to easily fight that infection off. I'm talking about ones and twos rather than hundreds and millions of bacteria. That's the reason for that. And, so understanding that what comes out of your tap isn't sterile but sanitary allows for the understanding of why we need submicron filtration and may need to protect commercial applications from these ones and twos of bacteria. So what are those types of contaminants again? Ionic. This is your dissolved minerals, such as calcium, magnesium, iron, any of your heavy metals, lead, copper, you name it. If it's in your water supply, It's because of that acid rain dissolving these minerals into it. And this is your charged stuff. This is what makes up total dissolved solids. Particulate. This is the category called turbidity. We measure, this is the garbage can we throw all the dirt load into when we measure it. This doesn't tell us anything about what type of dirt it is or its size, okay? We just measure how dirty the water is, and this is done by shining a beam of light through it and measuring how much light makes it through the water. The more light that makes it through, the cleaner the water. The less light that makes it through, the dirtier the water. These are measured in NTUs. This is everything from sand, oxidized iron, frogs, logs, and twigs, your organic particulate, your bacteria and cysts. These are all physical particles we can separate with filtration products. Now, organics, this is the result of the byproducts of sanitation, the decay of organic material. If you've ever had a really bad glass of red wine where it's really bitter and tannic tasting or off tasting, that's from tannins. Tannins are a group of acids that are created from a breakdown of organic matter. And depending on the type of organic matter you start with and the environment in which it breaks down, we produce tannins or other organics in the water. And then we have chemical byproducts. All of our organic chemistry that we produce in industry may end up here as well. This is oils. I mean, organic chemistry covers the breadth and the breadth of all of human experience when it comes to all of our compounds in the water. This is from food products to industrial synthesized chemicals. And we measure this under the category of total organic carbon. And then we break that down into volatile organic carbon, which is stuff that's light enough to gas off on its own at room temperature, in sort of a generalized description there. Think of potpourri. You know, you've got a bunch of organic material sitting in a little bit of water and it's gassing off that odors and aromas. Those are volatile organic chemicals that you smell. Because volatile organic chemicals sounds sinister, doesn't it? But all it means is stuff that can easily evaporate in the air that are organics. And then there's soluble organic compounds. These are compounds that are organic that stay dissolved in water. That brown water you get from leaves sitting in puddles and sort of stuff, that's what we're talking about here as well. Now, the other one we have is microbiological. This is your cysts, bacteria, and viruses that are all waterborne pathogens. This covers a lot of ground here, but this is stuff we can mechanically remove or chemically treat to get rid of or disable. And the final one is dissolved gases. We don't focus a whole lot on these in water treatment. Why? Because most of the time these will gas off over time, but there are some industries where dissolved gases are critical. Think of high purity water applications, process plants where they're heating a lot of water. Dissolved oxygen, oxidizer, this is where we get the term oxidizer from, is oxygen. It's what creates rust out of iron, steel sitting out in public. Dissolved oxygen in the water is a very powerful corrosive agent. So in some applications, dissolved oxygen is great. We're using it to help get rid of things and break things down. And in other applications, we don't want it there. Hydrogen sulfide is one of the rotten egg smell that can come from rotting organic matter or from gas deposits or breakdown of sulfate containing rocks from the acid rain. Maybe part of how we get sulfide into or sulfates into the water supply. And then there's dissolved CO2. Dissolved CO2 may be part of the natural gases in the air or the breakdown of carbonates into CO2 and gassing off. And then there's methane, which may result in wells from drilling and those sorts of processes, intersecting those sealed gas pockets while we're looking for water pockets, those sorts of things. So understand that our hydrologic cycle, a lot of it has to do with this gas right here. Because CO2 is the building block chemical that creates carbonates, which creates calcium carbonate, because carbonate is CO3. And we bond CO3 with rocks to form carbonate scales. And when we add acid to CO3, we get oxygen and carbon dioxide. So the alkalinity buffer system, that cycle, is incorporated into all of this. And it is the linchpin of rock getting into solution and coming back out. So this is all linked to some really important foundational chemistries in our environment. So when we start talking about contaminants, how we get rid of them, we're going to start with solids. Why? Because these are the easiest things for us to approach, attack, and remove from solution. A human hair is about 75 microns. What's visible to the human eye is right around 40. And cysts range from size from 1 to 4 microns. The reason we focus on cysts is because cysts are the eggs of certain bacteria that have a hard shell around them that protect them. And they require much more chlorine to break down. They're more chlorine resistant than their parent bacteria. Their parent bacteria can't survive sanitation, but cysts may. It's one of the reasons why we have submicron filtration, is to make sure we capture these little eggs in our water supply. Remember, we have a sanitary water supply, not a sterile one. And a micron is 1/25,000th of an inch. So we're talking about a very, very small items here. So turbidity includes floating particles. This may be dirt. Think of dust in the air. You know how some of the dust settles out on furniture and stuff, but a lot of other parts of dust still float around. Well, the stuff that's still floating around is your colloidal particles, right? Well, think about a pipe kind of like the wind blowing over a desert here. If you've got some of this floating particles, when you're not running water, have settled out to the bottom of the pipe. Well, now we have some stuff that's still floating in the water. That's your colloidal stuff. But when we turn on the water flow again, that flow may pick up some of that stuff that's settled out in the pipes and stir it back up. And it's going to keep moving down, kind of like sand and debris does down a river, but that colloidal stuff stays there. Sometimes that's manifest as ferric iron and oxidized rust, particulate as well. And depending on how you form that stuff, it may be colloidal or it may be heavy enough to fall out of solution. We want to manage this dirt load and remove it with relatively cheap sediment filters compared to the rest of a treatment train. Manage dirt load cheaply. Why? It's your dead frogs, logs, and twigs. Very, very easy to manage and mechanical means to do that. Now, other solids that are microbiological, we're going to solve those in various different ways. Heterotrophs are bacteria and viruses and things that are not harmful to us to consume. Those are generally harmless, and there'll be some bacteria, some fungus, some algae, and some mold spores are all harmless. One of the most common harmless ones that we see that's a real nuisance in water treatment is the stuff called water mold or slime molds. This is actually a bacteria that produces a mucus coat. And this mucus coat, in order to get rid of this stuff, demands a high level of sanitizer to break down. And this stuff will inhabit dead legs and plumbing and keep growing. Where this becomes problematic is when you have too much of it and it clogs your filter systems. But B, if you get some of these other bad actors, the bad bacteria, pathogens, may inhabit the slime used to protect this bacteria, this mold from destruction in its environment. They may grow in there. So slime mold is something we want to get rid of out of our water supplies as well. And algae. This is a great illustration that our water systems aren't sterile. This is a 5-micron cartridge system from our Everpure group, and this is a phosphate feed bowl on the back end. It's clear, but algae made it through these filtration devices into this unit where it got enough light to grow. So algae can be a factor. We sell sleeves to cover these to keep the light out. We're not going to remove the algae because it's harmless, right? And there's typically not enough of it to impact anything from a taste perspective. But in a commercial application, that may be entirely unacceptable. So what we really want to manage is disease pathogens, right? Viruses, bacteria, and cysts. These are viruses, and these are orders of magnitude smaller than a cyst. The cyst is basically, Death Star sized compared to a virus. These are very, very tiny. This requires very special mechanical filtration to remove viruses. This is a membrane technology, either UF or RO will filter out viruses from water. Same thing with cysts and bacteria. But those aren't foolproof solutions as well. Remember, we're going to be constructing treatment drains based on the incoming water, not just a one-trick pony or the magic bullet of treatment. There is no such thing in water treatment. So sediment filters, these are basically based on the reduction of solids based on the size of the cartridge, the micron rating of the cartridge or system you select. Our Pentec line is rated from 1 to about 200 microns in rating. That's our product breadth offering. We do offer a lot of sub-micron filters as well, but they tend to be paired with activated carbon as well for more value. But remember, we're typically using sediment filters to protect more expensive treatment train items after it, like backwashing filters, carbon filters, UV, ozone, whatever system after it tends to be more expensive than a sediment filter. This is our cheap, getting rid of the gunk sort of treatment. Not that this doesn't improve water quality greatly, it's the starting point, and it's the cheapest point that we can improve water. Most of our Pentec filters are offered in a nominal particulate range. And what nominal ratings mean is this filter will remove 85% of the micron particle class it's rated for. So a 10 micron filter will remove 85% of the particles at 10 micron and everything larger than 10 micron. And the other thing is the devil's in the details with ratings. Why? Pentec filters, all of them perform in the 90 to 95% range in this function. That's where looking at NSF ratings is really, really important to understand and differentiate these products, or they're solely reduced to commodities. All right, the devil's in the details with this. So we're going to be separating out dirt load. But you can see by managing that dirt load, we leave our other treatment trains behind it, the ability to focus in on their function of like chemical reduction or ion exchange or reverse osmosis. We're going to protect those things from the dirt load. Okay, and we'll see why that's important here in a little bit. And this does no chemical reduction. It may do some organic reduction. Why? Because some of these materials are synthetic organic fibers without a charge. This may attract some, organics from the water, but that's not what it's trying to do. This is kind of like, the Tupperware in your dishwasher that leaves that oily film on it, doesn't quite get it off because it's too tightly held to the plastic. That's the kind of effect with organics you'll get here, but they're not rated to do that. They're not designed to do that. This is for dirt loading. Lots of different designs of these filters that will match a specific application. And depending on what you choose is going to be predicated upon your customer's desires or value statements. We do have, or had in the past, and have a sister company, Xflow, that makes ultrafiltration membranes that go in a backwashable system. And these systems can go down as fine as viral levels or better. So if you're looking for someone who needs viral protection, immune compromised patients, people that are rather paranoid about their drinking water, or industrial applications that may need ultra pure sediment free water, UF is a good way to go. It is backwashable and it filters down to the virus level in most cases, and it's certified to do so. So basically we're looking at various different sort of sieves, a colander, kitchen strainer, that can go to different levels based on the size of the holes in the strainer. Membrane technologies, both UF and RO, are all those same sort of sieves, those same sort of colander effects, but on a much, much smaller, tighter scale. Membrane technology is not chemical removal. It is physical removal, straining of the water. So understand that even RO is a physical, mechanical filtration step. We do have other mechanical filters out there, but you're noticing we're adding carbon to this. Why? Any media packed in a shape, in a tube or a vessel that you run water through will act as a mechanical filter. Slow sand filters have been used for centuries. Our water softening systems and backwashing carbon systems are there to do other things, but we backwash them to get the dirt load out of them. They're essentially 40 micron filters, but they still collect debris. So every filtration device used today is a mechanical filter, whether it's there for chemical removal or not. It's still going to act as a mechanical filter. That's why we put cheap sediment filters in front of our carbon filters. These are typically 5 micron in size. You can get sub-micron in carbon blocks. I don't recommending those. Why? They're going to clog really quickly. We'll see why here in a minute. These are made out of a dense carbon, and they're mixed with the resin and extruded out of a press, just like that Play-Doh press as a kid where you made a tube of Play-Doh. We're doing that with carbon here, and this also gives us chemical reduction as well, chlorine and organics. But if you use this as your main treatment device in an application, remember, only the outside surface of this tube is your mechanical filter. The depth and body of it is your chemical filter. But once you plug the outside of this, it's done. No flow is going to go through it once this is filled up with debris. So typically carbon blocks are paired with sediment filters in front of it to manage how much dirt load this surface sees. And based on those sorts of issues in the field, we create new technologies. Fiberdyne is a wet molded fiber structure like our depth filters, but manufactured in a special, our depth sediment filters. This is manufactured in a special way where we can incorporate additives to that depth filter modality, and we can create it. We vacuum mold a matte or fibrous wad of stuff in a slurry. We suck it around a core that gives that filter its absolute or its final micron rating for the unit. But essentially, we're creating a massive briar patch of material that the water has to flow over and around and through, leaving as much debris as possible and creating lots of paths to get through. And these are available in sub-micron and 5 micron. They hold significantly more dirt than a carbon block and have less pressure drop over time as it's related. We add all sorts of mixes to these slurries as we make these filters. We have powdered carbon mixes. We have specially select resins that get added to it. But at the end of the day, this is basically a mechanical filter that we upgrade with those other additives. We do have Fiberdyne blocks that we make without any additives like carbon. And it looks like this material down below. And what this does is it forces the water and its debris to basically snag, get caught up on all these fibers, and there's always another way through. The nice thing about this is that when water pulses it on and off, this will reorganize that dirt load to keep flow up. It's not doing it intelligently. It's just doing with a pulsing effect, allowing stuff to move internally with it and redeposit it internally. But with a carbon block, it's only this outer surface, which is going to be limited on how much that can do. Once it plugs up this outer surface, it's done. Where this block will have lots of pass through it, keeping flow rate up and pressure drop at a minimum. Fiberdyne is probably the best value per gallon of use that we have in our Pentec line. So for solid contaminants, let's take a look. For microbiological contaminants, we use disinfection, sanitation, and prevention. That prevention is our physical barriers. We use disinfection, sanitizers, and sanitation. We have UV and ozone from other groups that our customers may use to battle not only microbiological, but organics in the water as well. You have cysts, same applications apply. So we're also going to employ barrier methods, mechanical filtration in the submicron range to capture these very small biological creatures. And then there's the overall dirt load in the water that these critters are hiding in, sleeping on, resting behind, trying to avoid that UV light behind. We're going to use mechanical filtration to remove that. So we're moving on to the next class of contaminants, and these are chemicals that are introduced naturally. This is all of life, biology, using, depositing, excreting, breaking down, and running off into our water supplies or percolating through the soil. Okay? All of human history has water filtering through it and dissolving it slowly into our water supply. And this ends up in the form of organics in the water, and that's total organic carbon. This is taste, odor, and color. This is when you get that brownish or yellowish looking water that has nothing to do with iron. That's from those dissolved organic chemicals. Most of those are tannins, have a funny, musty, fishy kind of smell to them. This is, the kind of smell when you're going to a lake and you go swimming and you find the muddy section off the beach. The sandy beach section is that black, thick, oozy mud. Well, that black, thick, oozy mud is decaying organic matter, and it'll give off those funky smells. That's what we're talking about here. This is basically caused by decaying vegetation or animal matter. This becomes food for many of those microorganisms in the water. And this is all measured in parts per million or milligrams per liter. These two units are interchangeable. They're mathematically equivalent. So how do we get rid of all those organics in the water? Filtration and chemical oxidation. These are chemicals that we introduced intentionally at the water treatment plant. These are our sanitizers: chlorine, chloramine, chlorine dioxide, hypobromous acid, which is the bromine analog of bleach, ozone, UV. Lots of methods are used to sanitize water. We end up with, typically when it comes to chlorine, we have a total chlorine measurement that we take, and this is a measurement of combined chlorine with free chlorine. Combined chlorine is dirty chlorine. This is the chlorine that's stuck to all those organic compounds, and the free chlorine is the stuff breaking down those compounds and everything else in the water. And you'll get free chlorine reacting with combined chlorine until you break down the organics into either chloramine or trihalomethanes, or until you can break these down even further. This takes a lot more oxidation to do to break those off into regular methanes and gas off. But chloramine is something you're really familiar. You think of it as that swimming pool smell. When you walk into an enclosed swimming pool environment, that chlorine smell you're getting off the water is actually chloramine. This is a nasal and eye mucous membrane irritant. It's the reason your eyes get red and your throat gets sore after swimming. But this is also an effective sanitizer. Not as effective as bleach, but it lingers in warm water supplies longer. This has a 98% kill rate in a specific amount of time, and this is around 80 to 85%. But it sticks around longer. So it has a cost benefit ratio here that's better than chlorine in especially warm surface water sources where this is important. About 62% of municipalities now use chloramine in one form or another in their municipal treatment plants. So what are we using these sanitizers for? For oxidizable matter. And what does that mean? Everything in the water we can oxidize, from metals to organics to other sanitizers in the water you can react with. Chemicals aren't intelligent. They react with what they can bump into and if they're capable of reacting with it. So understand we're going to add this stuff in relative amounts of excess to break things down to leave us a residual that helps us maintain sanitary conditions in our plumbing. But these are chemicals I don't want to consume. I want these out of my water supply when it's time to drink. So high chlorine levels with high organics equals trihalomethanes. This is another reason for chloramine use. Chloramine does not produce trihalomethanes. Trihalomethanes are carcinogens. Most of the known organic chemical carcinogens known to man are all halogenated hydrocarbons, carbons with hydrogen stuck to it. This is almost all organic life or compounds, oils, things like that. When you add chlorine, bromine, iodine to them, they do some nasty things to the body. That's why we don't want to consume these things. This is the benefit of treating your water. You can consume small amounts of these for your lifetime with very low risk. But then again, I don't like consuming carcinogens as a whole. So, what's safe versus what's ideal is a big, big window for us when it comes to municipal waters. Now, chloramine we discussed, growing in prevalence. This is moving into northern climates as well because of its cost efficacy. But there is issues with chloramine. This is a nasal eye and ear irritant. Your red eyes from the pool is from this stuff. This will also react with copper plumbing if it lingers in the pipe too long, dissolving copper. Some people are really sensitive to amines, skin-wise, can cause skin irritations. So this is, one of those balance back and forth issues with sanitizer selection. There is no great sanitizer to use because they all have issues related to them. That's why I want to have this in my water until I go to use my water, and then I want to remove it. Now, chemicals that are unintentionally introduced to our water supply. Now, this is all of human existence, right? You've got pesticides, you've got herbicides, you've got fertilizers that are sprayed on our fields. My favorite time of year where I live is the time for all the liquid pig poop to be spread all over the fields for fertilizer. Great volatile organic chemicals coming off those fields at that time of year, plus the biological stuff going on, producing smells. You have pharmaceuticals. This comes from human waste. After ingesting pharmaceuticals, trace amounts come out. Also, people flushing them down toilets, disposal programs, waste streams from commercial pharmaceutical industries. These all end up going to our wastewater treatment plants, where some of them may be removed, some of them may not. Some may come out in the sludge that is then spread on our fields for compost at that point in time. Now, the issue with pharmaceuticals isn't how much of them there are. It's how little of them it takes to have an impact. If the last time you looked at your pill cabinet, think about your multivitamin. How many chemicals and nutrients are contained in that little pill? That tells you how potent chemicals are in the human body. Same thing with your, Claritin. My son takes that pill is, a speck compared to other pills. Why? Nobody wants to take a pill the size of a golf ball, right? Pharmaceuticals are incredibly powerful and potent chemicals, so we can take them conveniently and effectively. Well, that ends up in our drinking water supplies, rivers, lakes, and streams, and we need to manage that as well. This issue, to give you the scope of it, the Ganges River in India in the 90s had so much birth control from people flushing it down and just going to the bathroom. And their waste systems tend to discharge directly into the river. They had fish changing their sex from male to female based upon the amount of synthetic estrogens in the water. So this has profound environmental impact, and we want to get these compounds out of our drinking water supply. Why? They're incredibly powerful chemicals. One of the reasons why I'm a big fan of drinking water ROs everywhere. Now, we also think about this lovely little oil slick. I've got one of these growing in my driveway for my son's truck. But think about all the leaky vehicles, all the runoff of your roofs, the paint overspray from somebody painting their house, the fumes from that. All of that gets washed down in the rain and runs down into our lakes, rivers, and streams and percolates through the soil into our aquifers. PFAS is an example of this right now. That's percolating through the soil, ending up in our water supply. This is a visual of a discharge pipe. This one actually happens to come from Israel. But if you think about the great strides that North America has made in reducing pollutants, we actually lead the world in discharge requirements for industrial manufacturing. There's lots of places around the world that are discharging. This is black and greenish water that's reacting chemically with something here to produce a yellow brownish stain. Something is in this water, right? Well, this is now somebody's drinking water source or their food source for their fish or their aquaculture, their farm, their produce. This is why we need to manage these things. Industrial applications manage incoming water and effluent water, outgoing water. And the outgoing water, typically at North American manufacturing facilities, is typically cleaner than the water coming into it because of these legal requirements. A lot of U.S. manufacturing communities based around rivers up and moved in the late 70s and early 80s because of these discharge standards. They couldn't afford to upgrade plants to meet these standards. So these regulations have economic impact, but this is also economic opportunity for us. Why? Because we know this is a looped system. That contamination is going to be there. We're going to have to treat that water over and over and over again. These are unintentionally introduced, but they are there. So how do we reduce chemicals in water? Well, the most prevalent one we use is carbon filter design systems. Why? Carbon adsorbs carbon. Carbon like dissolves like attracts like in chemistry. Nonpolar organics or slightly charged organics like carbon. That's why we use activated carbon as our media. It's going to attract that carbon stuff out of the water. That's why we use it. Now, this is all predicated on design. We can do chemical reduction with other systems like RO and UF, but that's going to be economically challenging where activated carbon is cheap compared to it. So we're going to predicate our system design, A, on flow rate. How fast are we using water? Why? Because all of these chemicals represented in this picture, all of this stuff, pesticides, herbicides, pharmaceuticals, every individual pharmaceutical, every industrial pollutant, all this waste is all removed by activated carbon at different contact times based on its individual chemistry. So we use flow rate and water analysis to understand what we're going to remove so we can determine how much contact time we need with our activated carbon. All water treatment methods in a tube like this, whether it's softening or carbon or a cartridge filter, is predicated on a probability game, an odds game, and we're stacking the odds in our favor. We are trying to manipulate the flow rate and contact time as the water flows through the granules of media that we're forcing it to contact the activated carbon to give that carbon a chance to adsorb it onto its surface and hold it. And that's all about contact time, and that's about the individual chemical as well. We lump a lot of these chemicals into large groups to make this easier to do, like TOC, VOC, SOCs, right? We talked about that earlier. You have surface area and depth. How wide of an area do we spread our water over to get contact, and how deep of a media bed do we need to get that contact time? Both of these are critical factors in generating your appropriate contact time. And then with sanitizers, what we're doing with activated carbon is converting them. We're catalytically converting chlorine, hypochlorous acid, the sanitizer, into hydrogen ions, which is acid, and chloride ions. Basically, we're converting hypochlorous acid into hydrochloric acid, which is less damaging at the constituent level than the bleaches. The other things we're doing with chloramine is we're tying up the ammonia on the activated carbon and liberating the chloride ion off of that as well. 2 to 4 parts per million doesn't impact taste and odor profiles in the water. With all the organics, it's adsorption. This is like attracts like. This is that Tupperware bowl attracting oils. There's too tight of a bond there for the detergent to pull it off, so it stays. Well, we're using that effect with the water with the oils in it running over the carbon. The carbon is the Tupperware pulling that out of the water, sticking it to itself so we can backwash it off and remove it. This is what exhausts activated carbon. Why? Because the conversion process for carbon is catalytic and will go on far longer than your adsorption capability. So when it comes to chemicals, we're going to remove naturally occurring chemicals, intentionally introduce chemicals with activated carbon. We can do this with ROs and other membrane technologies, but we're going to use this much more affordable media first. Why? Because we really want to use and reserve special medias and technologies for removing the hardest things to get out of solution, out of the water. And that's dissolved minerals and dissolved gases. Now, what does dissolved minerals mean? This means total dissolved solids. This is anything in the water with a charge. Okay, there are some organic molecules that will carry a charge. They will play a role in this number as well. They tend to be slight in amount. But this is mainly your dissolved rock, which breaks apart into water into its dissolved salts. Sodium chloride exists in the ground as a rock, but when you add it to water, it breaks apart into sodium ions and chloride ions. The same thing happens with iron oxides. You get iron as a molecule dissolved in ion, +2 or +3 charged in water, typically, and hydroxide, OH minus, in the water. You get salts. All rocks are salts that can be dissolved with acid and get into water. Okay? So that's the mineral content we're trying to get rid of. Rain plus CO2 lowers the pH, makes it mildly acidic. Low pH rain dissolves rocks and gets minerals into your water. If you look at this river valley, from this point to this point all the way across between those two peaks, this was all eroded and dissolved by water. All this material filling in, everything down to the bottom of this stream, was dissolved and physically eroded into this stream of water. That's how powerful water is. TDS is measured in parts per million or milligrams per liter. Now, when we talk about that low pH dissolving rock, that becomes important. We need to understand what pH is. pH is essentially the hydrogen ion concentration. What does that mean? It's the amount of acid in the water. Hydrogen, when it breaks apart from its gas, H2, in water, results in H plus ions in the water. Hydrogen ions. That's acid. That's what we're measuring in water when we measure pH. And the P stands for a logarithmic scale base 10. So every number below 7 is 10 times more acidic than the number above it. The numbers above 8 are 10 times less acidic. The neutral number comes from 100% pure water and its dissociation constants. Okay, some chemistry there. What that means is water exists as H2O and also as H plus OH minus in water as a liquid. That reaction is going back and forth all the time between H2O and H plus and OH minus. And that rate is 7.0. And there's a lot of other terms behind it. So we base the scale off of. So when you have more acid, more H plus in the water than OH minus, you get acidic solutions. So 6 is 10 times more acidic than 7. 5 is 100 times more acidic than 7. 4 is 1,000 times more acidic than 7. So this is a very powerful scale. The other thing is this is where we get more OH in the water. Hydroxide can be good and bad, just like acid can be good and bad. It's chemistry. It doesn't know what it's doing. So if you look at these two pipes, this represents corrosion that can happen at both ends of the pH spectrum. This is acid attack on copper plumbing, and this is base attack, caustic attack on stainless steel plumbing at around 14. So realize managing pH is part of what we do as well, but we typically do it by managing the other contaminants in the water. Quite often we're not managing pH directly, some cases we are. But if you look at it, normal pH of steam is 7.0, but look at rainwater, it's down in the 5 to 6 range. Baking soda and seawater is up around 8.5 to 9. Ammonia is up around 12. Lemon juice is down around 2. Vinegar is down around 3. Concentrated acetic acid is down around 2. That's concentrated vinegar. And then battery acid. Acid rain is from the 1 to 5 spectrum. So realize pH plays a very important role in whether or not we will form scale deposits and whether or not we'll be able to have a lack of corrosion going on with our metals. And notice that we use the words increasing alkalinity here. Alkalinity is part of that carbonate, bicarbonate, CO2 buffer system. This is Tums in the water. This is the buffering capacity of water, how much acid it can absorb. You have to consume your alkalinity to make water more acidic. And this is increased acidity. So, why do we manage mineral composition in water? Principal reason is scale. We'll go into why. But just like when you studied the fire pyramid, that you need heat, fuel, and oxygen to make a fire, right? The same thing happens with scale. There's a recipe to scale, and that requires calcium or magnesium or iron, carbonates. So you've got metals and carbonates. And a third ingredient, dirt. I hate this in this representation because what this really means is nucleation site, a place for that scale to form. Any rough, bumpy surface is going to give you a place for scale to form. Your heating elements, those sorts of things. And we have to have a pH above 7. Why? Because carbonates cannot form under acidic conditions. Why? Because the acidic conditions are going to break this down into oxygen and CO2 and gas off. Okay? So, when we have pH above 7, hardness minerals and carbonates in the water will make limescale if we heat that water and it's above a pH of 7. Well, if you think about water softeners, we just take this ingredient out of this pyramid and it collapses. When we take reverse osmosis or membrane technologies, we're reducing this, and this to a point where they're no longer significant. They don't form enough scale to be a problem. You can also remove the carbonates. If you think of dealkalization technologies, if you're thinking about our systems friends, this would be our Claris technologies. It breaks down the carbonate and converts it to CO2 gas and gases it off. So you don't have what you need to bake your cake. You've got the flour and the milk, but you don't have any eggs. Any one of these you remove, you can't bake the cake. That's water management in a nutshell. You're pulling away something so you don't make the cakes. So these are 4 scale deposits from a 50-mile radius around St. Louis, Missouri. Lots of different mineral contamination in different wells and aquifers in that region. Geology plays a critical role in what contaminants are dissolved in your water. So what's the impact of that? Well, we measure this based on a parameter called grains per gallon, which is 1 grain per gallon is equal to 17.1 parts per million of that contaminant. Well, 7,000 grains equals 1 pound of rock approximately, very generic. Well, the average water supply in the U.S. is 15 grains per gallon. Mine at home is 23 grains per gallon. Well, that equates, if we heat that water up, at 467 gallons of water, you're going to have 1 pound of rock come out of that. My water heater, got 6 kids in my house, 23 grain per gallon hard water. I use a little over 200 gallons a day. It's going to take me 2 days to form a pound of rock in my water heater. Every 2 days, it's 132 days, 132 cycles. Every year on my water supply untreated, I'm going to create 165 pounds of rock in my water heater. That's why when you go to replace a water heater on untreated water, that thing weighs a ton trying to get it out of a basement. It's this relationship. And if your water's harder, you're making this faster. It's an important management tool. When we look at the opportunity as it's related to hardness around the United States, well, the U.S. Bureau of Standards says water is very hard over 10.5 grains per gallon. Well, that is the vast majority of North America right there. Anybody on the Great Lakes Water System or the Tennessee Valley Water Authority, which is a good chunk of North America and its population centers, are in this range, 7 to 10.5. This is Lake Michigan water, Lake Erie water, Lake Ontario water, TVA, Cumberland River, all the stuff, Tennessee, Kentucky, the Carolinas, Mississippi, Alabama, parts of Louisiana, parts of Georgia are all fed off of this water. Lots of markets for this stuff, even on surface water sources. So what does scale do? Well, this is what can happen with scale in high hardness conditions untreated. This is a 2-inch pipe from a Target store in Kalispell, Montana. This was a 5-year-old store, 40 grain per gallon hard water, untreated, coming into the cold water line. Had a softener on the hot water side. They had to repipe this building. And this is just from the temperature change from 52 degrees coming out of the ground to warming up to a 70, 75 degree temperature inside the store in 5 years. This is extreme, but this can happen. This cannot be removed efficiently from the plumbing and open this back up. This store had to be replumbed. That's a huge economic impact. Then there is the economic impact on heating and energy loss. Water softener is one of the greenest appliances you can own. Why? Because of scale production on heating elements and loss of efficiency and wasted gas per thousands of BTUs. Thickness scale, 1/16 of an inch. You lose 11.5% of your gas efficiency. Note, this is worse on electrical appliances. And you burn 1,000 cubic feet and you waste 110 cubic feet of gas. Or to get the same energy transfer, you need 1,110 cubic feet, as you did when you bought that appliance new. This is cumulative. 1/8 of an inch, 27% efficiency loss. 1/4 inch, 28.5 efficiency loss. 3/8 of an inch of scale, almost a 50% efficiency loss. So my 75% efficiency unit is now down around 35 to 37% efficient. I'm losing a lot of money on my gas bill here. Worse if it's electric. 1/2 inch of scale, 60%. Now think about that water heater full of scale with, 8, 10 inches of this stuff. You're heating a lot of rock before you heat water. This is profound economic impact. Remember, this is not just going to happen on that water heater, but this is going to impact every water heating device in a building. Now we have other means of mineral control in the water. We could do that chemically. Typically in potable water sources, we're going to use what's known as a polyphosphate or a scale control or scale inhibitor. This is great for tankless water heaters, good for small applications, commercially, like coffee bars and things like that, small ice makers. This is a sequestering agent. What this will do is it will tie up hardness in the water with phosphate instead of carbonate. This stuff will stay in water until it's completely saturated. It can bond up to 26 calcium molecules. It's very, very efficient. It's a threshold chemical. Very small amounts of phosphate can manage large amounts of hardness. It's only effective up to certain grain hardnesses where you trade one problem, hardness in the water, for precipitating out calcium phosphate. Soft, mushy scale, still plug things, but a useful compound in lots of ways. So if you want to know more about this, hit me up and we'll go through the chemistry of it and let you know how this really works and where it's used as a tool. But we offer these products in lots of different options as well. Now we're moving on to another aspect of mineral control in water called ion exchange. In this process, we're not removing or sequestering hardness from the water. We are removing it and replacing it with something else. Why? Because we want to keep the charge balance in the water. When you remove only 1/2 of the salts from the water, you can create very aggressive water. Why? Because all the negatively charged stuff in the water is going to look for something to react with. When you create that sort of imbalance, you create environments where other chemistries are going to take place. It's one of the reasons why we use ion exchange. So ion exchange is literally the process of on this resin bead. If you look at these squiggly lines, this is where the rest of this attaches to the bead. And it's all made up of all these chemical compounds. But the exchange sites are right here on this sulfonyl group for those that like chemistry. But basically, this offers a place where we can put things on and put things off this molecule. Your lungs work the same, your blood works the same way with hemoglobin using iron, where you bond oxygen and you swap it out for carbon monoxide or carbon dioxide, and then gas it off in your lungs. Same sort of process here, but in water. And if you notice, calcium has a +2 charge and sodium only has 1. This is going to happen in equal amounts of charge, right? For every charge we rip off the molecule, we need to put it back on. Notice you have 4 sodiums here on the bead. This is your resin in your tank. After regeneration, it's all ready to go. You pass water over with hardness over it, it's going to swap out the calcium on those sites for the sodium, and then the sodium goes downstream. Why is that important? Why? Because sodium does not form hard scales with carbonates. It doesn't, it eliminates the problem. We can't make the cake any longer. The cake we do make doesn't resemble a cake, it just falls apart. It's a white powder that wipes off easily, typically not big of an issue. Anything that has a more positive or a stronger positive charge than sodium will exchange on these sites. Things with a less positive charge or a more easily manipulated positive charge are going to be used in other forms of resin. You have acid forms where you put a hydrogen here. If you regenerate your resin with potassium chloride instead of sodium chloride, you're putting a potassium molecule here and exchanging it off. Lots of different resins on the market, and they have a lot more uses than just water treatment. But this is what we're doing in ion exchange. Okay, this chemistry here, and we'll go over this in depth in another presentation. So we're going to move on to the other physical way we remove total dissolved solids from the water. And with ROs, it's basically everything from the water. And we'll show you why here. Why? Because in an RO system, you have a feed water coming in. This is the water. The blue is the water. And we're running it through a tube with this membranes trapped in it. But think of the water as a 6-lane highway coming in, right? And we have one off-ramp, and that off-ramp is through the RO membrane, okay? But that's a really, really tight off-ramp. And the only thing that we really want to let through that off-ramp is the water. We may have some slightly, approximately the same size cars as water, or the right shaped cars be able to get through this RO membrane material. But what happens is, on the outlet side of it, we have that 6-lane highway narrowed down to 1 lane. And what you get is a traffic jam, a concentration of what's in the water. We're not removing the contaminants from the water, we're removing the water from the contaminants and throwing that away. Okay, this is basically nothing more than a colander at the water-sized level. And you will occasionally get a long compound that's the right shape to slip through. Kind of like you get the spaghetti sticking through a hole in the bottom of a colander. That sometimes happens with RO membranes with long molecules that are about the width of a water molecule, and they can slide through sometimes too. That's why you get percent rejections. But this rejects the vast majority of RTDS. This is a physical mechanical process where softening is a chemical exchange process. Two different methods. The vast majority of what we do in water treatment is a physical mechanical separation. And we do that in products like the FreshPoint or the GRO membrane system. And we collect that product water, the off ramp, as our permeator product, and we store it in a tank. Why? Because that off ramp is tough to get onto, and it makes water at a very, very slow pace. This technology is used to make all those concentrated products you see on your grocery store shelves as well. Concentrated detergents. We're pulling the water off and bottling the concentrate in those circumstances and recycling water. RO is used in a lot of different places as well, other than water treatment. Then there's another way we can get rid of dissolved solids in water. We can use chemical oxidation. For ferrous dissolved iron, this is dissolved trace amounts of iron. Trace amounts of iron will form that characteristic rust. It starts off clear in your water, it's dissolved, but when it gets exposed to air, it turns to that familiar orangey color and precipitates out if there's enough of it. Sometimes this will just make your water appear yellow or light brown in color if the particles are fine enough. Same thing happens with manganese, but this will create black stains or black particulate in your water supply. And then there's hydrogen sulfide gas. This will happen in shallow wells, surface water sources where you get that rotten egg smell from breaking down sulfur byproducts in organic material or from sulfur reducing bacteria. How do we solve these issues? Well, we oxidize them all. And in the case of sulfate reducing bacteria, we're removing its food source by these methods. We have the AIO system, 2510, which is a direct oxidation method using oxygen and a tank and some specialized medias, depending on how a customer wishes to assemble that. We have it in some of our industrial processes and commercial applications, ozone generating systems, and sometimes people pair those with an AIO system by pumping in ozone instead of air to make it even more aggressive of an oxidizing environment. We have control systems that have chemical feed pumps that will feed oxidizers like chlorine, hydrogen peroxide, and we have things that'll feed pH management chemicals as well. This comes from our swimming pool group, but we have analogous equipment in our industrial process lines as well. These are sensors and driven products as well. Then you have drop-in style cartridges that are select special resins that will oxidize this material. These are things like green sand cartridges, other oxidative catalog sort of media types that are put into these products to target iron and manganese in small, low flow applications. So what we're doing here is we're oxidizing something that's dissolved into a filterable solid. You can see the result of water just being exposed to air in this float tank. It's dropping out. Well, that's what we're manipulating here and using as our tool for treatment. This is a chunk of manganese with a bunch of other stuff mixed in. It's a black precipitate. This is the stuff that barnacles up inside of galvanized plumbing quite often. And we can do this oxidation via various different methods. Chlorination, manganese green sand, which has permanganate on it as the oxidizer. Aeration, ozone. We can oxidized ferric iron, not recommended by reduction by softener. What we mean by this is iron reduction by cation exchange has reasonable practical limits for which we do that with. Why? Iron can be much more tightly held inside a bit of resin and have a very hard time coming off. Things with a +3 charge and larger have a harder time being removed from resins because you have more atoms, more resin bead particles or reaction sites holding that +3 iron or +3 aluminum to it. and it's harder to break it, and it's formed a structure that's harder to get sodium around to push it off. So understand iron is a special case, and we really need to understand the water chemistry there to select the best method of removal. Quite often we use oxidation and softening to manage iron issues. So for dissolved gases, we have ferrous iron, manganese dissolved, hydrogen sulfide gas. Well, what are we going to do? We're going to oxidize those chemicals and then use mechanical filtration to remove them. We can use scale inhibitions like polyphosphates to chemically treat these things in the water. Mineral scale. We can use scale reduction technologies like reverse osmosis. We're eliminating the amount of material you can make a cake from. And in softening, we're taking the eggs out of the cake, so you can't make a cake there. So lots of different technologies, all can be paired together in treatment trains to address the water quality you wish to produce from the source water you start with. That's why it always takes somebody who understands the application and the entry water level to understand where you need to get it. Basically, in water treatment, you give me the end spec, you give me what to start with, and I will give you the technologies and a treatment train that will get you there. And our job is to create the most effective and efficient treatment train, both from a cost and a performance standpoint, based on the incoming water and the desired results. There's a lot of ways to skin the cat in water treatment. That's what makes this so much fun and gives us so much opportunity to perform better than our competitors by paying attention to the details. So we can outcompete, meet our customers' expectations, and give them the water quality they want. So thank you very much for attending. We're going to go ahead and stop recording now. If you have any questions, feel free to reach out to Mark or I at training.request@pentair.com. Thank you very much for viewing this. And if you have any questions, let us know.